Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, we looked at some of the implicit schemes in the last class, and we saw that the implicit scheme allows for a higher delta t. We will look into the theory of why implicit schemes allows the higher delta t, but before that I would like to introduce some more numerical schemes to you, and then we will go into the theoretical part of something called lax equivalence theorem, where we say that there are some properties of the scheme or the solution which are basically the consistency, stability and so on and so forth, which basically tells you in what conditions you will have the stable and accurate solution. Okay. So, before going into that, let us look at some of the more popular schemes that we introduced at the end of the last class. So, one is the leapfrogging scheme. Okay. So, leapfrogging scheme is also called the basically central in time and central in space. Okay. So, if you take the convection scheme, for example, C del u by del x equal to 0. Okay. This is your convection problem. So, if you use a leapfrogging scheme, okay, this is basically central in time and central in space. So, if you use central in time, this is u I n plus 1 minus u I n minus 1 by 2 delta t, right, plus C u I plus 1 n minus u I minus 1 n by delta x is equal to 0, right. So, if you reorganize it, okay, so you can get u I n plus 1 will be equal to u y n minus 1 minus c delta t by del x, that 2 this will be 2 will cancel out. So, minus lambda u I plus 1 n minus u I minus 1 n, right. Now, if you look at this scheme closely, you can basically derive any scheme that you want. As we have discussed, you have the general discretization scheme, you can take as many stencil as you want and derive your scheme, but that scheme should have some meaning, okay, and it should serve some purpose. So, here the leapfrogging scheme is, if you look at the structure of this scheme, okay, so this is my nth point. So, this is, let us say this is my x and this is my t, right. So, if you are starting, you know the value at n, right. So, let us say this is my point I, and this is I plus 1 and this is I minus 1. Okay. But this is scheme requires your value at n minus 1, right. So, of course, you do not know the, if you are starting a simulation, you do not know the value of n minus 1, right. So, this is not a self starting scheme. What does it mean? That means that you have to start solving this problem using some other scheme, maybe the forward in central in space or forward in time and backward in space, whatever, and so that you can get the values of some time steps. Okay, and after that you can start using this leapfrogging scheme, because then you have the value at n minus 1 also. So, let us say you started at t equal to 1, 2, 3 and up to 10 you have solved the using the approach which is FT, let us say FTBS. Okay. And then from time step 11 you can switch to the CTCS or leapfrogging scheme, because you know the value of 10 as well as 9, okay, to get the value of 11, right. So, you know the value, you need the value at so if you want to calculate the value at 11. So, let us say this is the value at 11. So, you need the value at 9, right. So, n plus 1 if you want to calculate, you need to get the value of n minus 1, right. So, this is not a self starting scheme, but you can use another scheme to start your simulation and then you can switch to this scheme, and you have to do a big bookkeeping, so that you have the values at n minus 1 available when you are trying to use this scheme, right. So, if you want to calculate the value at n plus 1, so this is your n and this is your n plus 1, okay. And this will be your value. So, this is my I at n plus 1, I plus 1 and I minus 1, okay, and this is the value at n minus 1, right. This is I plus 1 and I minus 1, right. So, what is the value that you want to get? You want to get this value, I will use the red color here, u I n plus 1, and what is the value that you need? You need u I n minus 1, and you are basically you have the unit value at nth time step I minus 1 and I plus 1, right. So, if you connect this, okay, to get these values you need this and this and this, okay. So, it's basically it looks like a frog and basically jumps the step, right. You can see that it is you want to get the value at n plus 1, it is jumping from n minus 1, right. So, that is why it is called the leapfrogging scheme, it leaps, okay. So, this is called leapfrogging scheme, and there are some stability properties of this scheme which is superior to the explicit scheme, and that is why these schemes are used in the simulation. We will look at the stability of criterion of these schemes, also perhaps solve some problem. Okay, the another scheme that you have is basically the Lax-Frederick scheme. Okay, so, this Lax-Frederick scheme, this is forward in time and center in space, okay, but we take the average of I plus 1 and I minus 1. So, why we need that? See, you know that FTCS is not stable, right, forward in time and center in space is not stable, that we have seen for a linear convection problem, right, not for the diffusion problem. So, we are using this for the linear convection problem, okay. So, let us look at that scheme, Lax-Frederick scheme, okay, we will call it LF, okay. So, your problem is del u by del t plus C del u by del x equal to 0, okay, and you can write it as del u by del t is equal to minus C del u by del x, okay. And what Lax-Frederick does, the usual approach, let us say if you use FTCS, right. So, this will be u I n plus 1 minus u I n by delta t will be equal to minus C u I plus 1 n minus u I minus 1 n by 2 delta x, right. This is your FTCS scheme, or you can write it as u I n plus 1 will be equal to u I n and minus C delta t by 2 x 2 delta x, okay, u I plus 1 n minus u I minus 1 n, okay. So, this is your FTCS scheme, but if you use this scheme, as we know, we have seen that for example, the problem that you have solved, okay, we had lot of wiggles here and this portion, right, and eventually if you keep on running this problem, this will eventually blow up, right. So, FTCS scheme is not suitable for the convection problem. So, what the Lax and Frederick proposed, they were through famous scientists, they said that instead of using u I n, we use, so now it is called the Lax-Frederick scheme. So, u I n plus 1. So, you use the average of u I n and u I n plus 1, right. Let me just see. No, so average of central, not the time, okay. So, the time stage remains the same, okay. So, this is basically u I plus 1 n plus u I minus 1 n minus C delta t by 2 delta x u I plus 1 n minus u I minus 1 n, okay. So, that means, so you are taking this value as u I n, this is your I, and you are taking the value of u I n. So, we replace it back with this is I plus 1, this is I minus 1. So, you replace the u I n value as half of u I plus 1 n and plus u I minus 1 n, okay. And then you got a new scheme, and this scheme is basically stable, okay, conditionally stable, but it is stable, it is not unconditionally unstable like the FTCS scheme, okay. So, we will look at the property of these schemes also. So, I am just introducing a class of schemes which are very popular, okay, and we will look at the stability properties of these schemes in future classes. Okay. The last one that I want to introduce, of course, there are many more schemes than what is written here. Okay. I am just introducing a few to you, okay, which are very popular. So, the third one is the Lax Van der Waals scheme, okay, and this again Lax and Van der Waals have proposed this scheme. So, this is also FTCS, forward time and center in space, but we use a second order numerical diffusion. So, these terms are basically additionally added. Okay. So, let's look at the FTCS scheme. Okay. So, I can work it here only. So, this is my FTCS scheme, right. So, retain that, but add a second order term. So, that will become your Lax Van der Waals scheme. Okay. There are two kinds of Lax Van der Waals scheme. One is the two step Lax Van der Waals. Okay. We will look at that scheme also later. So, this is the one step Lax Van der Waals scheme. This is u I n plus 1 will be u I n minus C delta t by delta x u I plus 1 n minus u I minus 1 n, and then you add some basically numerical diffusion, because this is not stable by itself. Okay. So, delta t square by delta x square, okay, and if you are adding a diffusion, the diffusion terms are normally the second order accurate terms, that is basically u x x, okay, or delta u by del x square. Okay. This is the nature we have seen in the diffusion problem also, when you have dl u by del t equal to nu delta u by del x square, right. So, nu is basically you can equivalent it as c square delta t by del x square, and you have to use the central differencing scheme for that. That will become u I plus 1 n minus 2 u I n plus u I minus 1 n by delta x square. Okay. So, this is your Lax Van der Waals scheme. Okay. So, this is the FTCS, forward in time and center in space, but then you have added some diffusion term here. Okay. So, that delta x square I have written it twice. Okay. So, this is how it will look like. Okay. You can have sign, you can use other sign also. Okay. So, c square delta t by, okay, there will be, you can use the two term, okay, or you can replace this entire thing with a another diffusion term of your choice. Okay. So, the purpose of this term is to basically make the scheme stable. Okay. The central differencing scheme is not stable because it does not have any diffusion. Okay. For any scheme to be stable, it should have some diffusion, but if you have, it has got too much of diffusion or too much of dissipation, it will basically smear out any non-linear phenomena, okay, which is also not something that you want. So, you want the scheme to be stable, but at the same time it should be accurate enough to predict the flows accurately. Okay. So, we will discuss these schemes stability characteristic in the later classes. Okay. For now, what I want to do, I want to go to something called understanding these schemes, and want to see that when we discretize the scheme, what is the actual PD that you are solving. Okay. We are trying to solve this PD, okay, but then when we discretize it, we are actually not solving this PD, but a modified PD. Okay. So, we will look at those approaches, I mean those equations, and that will give us some understanding that why some schemes are stable and some schemes are not stable. We have been talking about the diffusion term, right. What do you mean by diffusion term? Okay. How does it add stability when we use the backward differentiating or forward differentiating, basically the upwinding scheme, but when we use the central differentiating, that disappears and we get then unstable solution. Why does that happen, right? So, let us look at that MPD scheme, basically modified PD equations. So, we will start with the convection problem again, del u by del t plus c del u by del x equal to 0, okay, because this is the most complicated problem. The diffusion problem is stable because there is anyway it is just diffusing, and as long as your viscosity or the numerical diffusion term is positive, that it will be stable. But the more critical problem is your the linear convection. Okay. In the diffusion also you have to honor this the diffusion Courant number, but that is normally not that restrictive in a flow problem. Okay. So, if you write this in FTCS, okay. So, if you try to do this in FTCS, work this out. Okay. So, we have a scheme del u by del t plus C del u by del x equal to 0. Okay. And we are doing it using the forward in time in center and space. So, this is basically u I n plus 1 minus u I n by delta t plus C u I plus 1 n minus u I minus 1 n by 2 delta x is equal to 0. Okay. So, there is something called consistency of the scheme. Okay. So, the any scheme that we are using should be consistent. Okay. What do you mean by consistent? That means that if you reduce the delta t and delta x to 0, basically if they tend to 0, your the discretized equation, okay, should lead to your PDE that you are trying to solve. Okay. So, that means in other words, so when we have discretized in this form, we have basically let go of some of the truncation error terms, right. Remember, there will be truncation error term in this also, which will be order of delta t, and there will be truncation error of this term, the leading truncation error will be order of delta x square, right. So, we have basically let go of those terms, right. So, we have to make sure that if we in those terms, if you put delta t tending to 0 and delta x tending to 0, it should become 0, the truncation error should go to 0. So, truncation error should go to 0 as delta t and delta x goes to 0. Okay. That is what mean by the consistency of the scheme. Okay. So, let us look at this problem, okay, and look at what is the truncation error of this scheme. Okay. So, earlier we have taken the seen the truncation error for let us say del u by del t separately and for del u by del x separately. Okay. But now we are looking at the truncation error of the scheme itself, the entire thing when we consider together what is the truncation error that we are getting. Okay. So, how do you do that? Same our good old friend Taylor series will use that and we will find out what is the truncation error of the scheme. So, this is u I n plus 1 will become u I n, okay, and plus delta t. So, now you see when you are writing this Taylor series, so earlier we have used u prime and so on and so forth, but now we have derivative with respect to time also and with respect to space also. You will have del u by del t term and you will have del u by del x term and all their higher orders and so on and so forth, right. So, what I will do, I will use a notation. So, I will say u t that represent del u by del t, and when I say u x it will represent del u by del x. And similarly, if I said u x x, then it will be del to u by del x square, u t t will become del to u by del t square. Okay. So, I will use this representation for my Taylor series expansion. Okay. So, this will become del t u t I, okay, and this will be at n del t square by factorial 2, okay, u t t I, okay, I is at ith place at n plus del t cube by factorial 3 u t t t I n and so on and so forth, right. So, what we did, we expanded our n plus 1 around n, okay, and we know our delta t is basically the jump from n to n plus 1, that is our time step. Similarly, these things we already know, u I plus 1 n will be basically u I n. So, everything I want to expand around u I n, okay, plus delta x, this will be u x I n plus delta x square by factorial 2 u x x I n plus delta x cube by factorial 3 u x x x I n and so on and so forth, and they have u I minus 1 n will be u I n minus delta x u x I n plus delta x square by factorial 2 u x x I n and minus delta x cube by factorial 3 u x x x I n and so on and so forth, right. So, now use this and put it back in this one, right. So, when you do that, so what I will do, I will basically rearrange these terms. So, I will take this minus this and divide by delta t, okay, and that will give us the term. So, if I use that term, so I am trying to approximate this portion first. So, that will look like u t I n plus delta t by 2, okay, u t t I n, delta t square will get cancelled with delta t here, because I am dividing by delta t also, okay, and plus delta t square by factorial 3 or 6 u t t t I n, okay, and plus some other term, okay, just let us retain up to this third term only, okay, and then we will have plus c, and I am now expanding this, okay. So, what I am doing, so I have, let us, if I call this a, b and c, okay. So, I am doing b minus c by 2 delta x, okay, and using the value that gives us the this values, okay. So, that will become c u x I, okay, and this thing will anyway get cancelled out, okay, plus delta x cube by 3 u x x I n, and then will be the next term will also get cancelled out, and you will have something like delta x 5 to delta x 5 by factorial 5, right, u x x x x x I n and so on and so forth, right. So, this is our value, okay. Now, if you rearrange it, this will become, so I am collecting this term and this term, okay. So, this is u t plus c u x I, okay. U t plus c u x is what? U t is plus c u x is basically del u by del t plus c del u by del x, okay, is equal to, this entire thing is 0, okay. So, that will become minus delta t by 2 u t t I n and minus delta x cube by 3 u x x I n, and then plus or minus does not matter, okay, order of delta t square and delta x to the power 4, okay. So, there is an error here because we are dividing by delta x. So, this will become delta x square and this will become delta x 4, okay. So, this is delta x square and delta x 4, okay. So, this is what our term looks like, okay, by just putting this value and putting our Taylor series expansion, right. So, if you look at, this is the equation that you want to solve, and the right hand things that you see is basically our truncation error, right. So, for this particular scheme, so when you take delta t tends to 0 and delta x tends to 0, you would see that the entire term on the right hand side goes to 0. That means that equation is consistent, okay. So, our forward in time and central in space is a consistent scheme. It may not be stable, but it is a consistent scheme, because as we reduce our time step to 0 and our spatial size to 0, we recover our scheme, which is del u t plus c u x equal to 0. Okay. Now, when we are saying that we are using this scheme to approximate our linear convection equation, right. So, basically we are solving this problem, right. So, let me just write it in the next one. So, we are solving del u by del t plus c del u by del x I is equal to minus delta t by 2, okay, u t t I n, okay, and minus let us leave other terms. Okay. So, that will become order, or just let me just see a second. Okay. So, that will become delta x square. Okay. We have written a delta x square by 3. So, just return that term. So, order delta t square delta x square, right. So, now what we have done, we have put all these terms together and we are just returning the first term here. So, when we are trying to solve using our FTCS scheme, we are basically solving this problem. Okay. And you can see that we wanted to solve del u by del t plus c del u x by equal to 0, okay. But the right hand side is actually not 0, it has got certain terms, right. Now, what we will do, we will write everything in terms of the space. Okay. So, this is u t t I. So, u t t is we want to put in terms of space. So, you have u t plus c u x equal to 0, that means u t is equal to minus c u x. Okay. So, I will take another derivative of respect to time, so u t t equal to minus c u x t, right, and you can replace it minus c del by del x u t, right. This is what it means, that will become minus c del by del x and u t will become minus c del u by del x, right, same thing. So, that still become c square u x x, right. So, u t t is equal to c square u x x. Okay. So, this equation can be written as del u by del t plus c del u by del x I is equal to minus c square delta t by 2 u x x I n plus order delta t square delta x square. Okay. So, we wanted to solve a problem which was basically del u by del t plus c del u by del x equal to 0, but because of our choice of our discretization scheme, which is forward in time here and central in space here, we got a scheme, we are solving an equation which is looking like this. Okay. So, this equation is called the modified or exact, sometimes exact also, modified partial differential equation, modified PDE or MPDE. What is it exactly? This is basically when we are using a certain discretization scheme, it actually modifies the PDE, okay, and instead of solving this problem, we are solving this problem, right. Now, if you look at this equation closely, okay, ignore this the higher order terms, but look at the just the first term. Okay. So, this you will see it looks like del u by del t plus c del u by del x is equal to nu del to u by del x square, right. So, the u x x is this term, this is u del by del x del u by del t. So, this is not, we are not solving a convection linear convection problem, but we are solving a convection diffusion problem because our choice of the diffusion scheme. Not only that, you will see this term, the nu here, if you compare to this one, the nu is equal to minus c square delta t by 2. C square is a positive number, delta t is a positive number and there is 2. So, this entire thing nu is negative. So, that means you have negative diffusion, right, your scheme has got a negative diffusion. And earlier we have seen when we are trying to solve the problem of the diffusion, we saw that when the nu is negative, the numerical diffusion term is negative, it basically blows up very, very fast. And that is precisely the reason why you are not able to use the FTCS scheme in solving your problem, your linear convection problem, because the schemes gives you a negative diffusion, okay, and that leads to the blow up of the scheme. In the next class, what we will do, we will look at the FTBS, okay, forward in time and backward in space, and we will get this same modified PDE, okay, for that particular problem, okay, and we will see at what condition they become stable. So, we know that FTBS is stable, okay, from our experience for a linear convection problem, if the C delta T by del x is less than 1, right, by just solving the problem, we know that, right. But can we also notice in our modified PDE? Okay. So, we will look at that FTBS scheme in the next class. Okay. For now, you should go back with the message is that when we are trying to use a discretization scheme on a given differential equation, okay, we basically when what we are solving is a modified differential equation, and we have to look at those terms closely to know about how the schemes would actually behave. Okay. With that, we will stop here. Thank you very much.